Welcome to the fall term in the beginning of this academic year's colloquium schedule. We've been pretty hard at work behind the scenes for the last couple of weeks, maybe scrambling a bit. But we've got a beginning lineup, and we'll try to keep you a little more abreast of who the upcoming speakers are in the next few terms. Today, I'm speaking to you myself to tell you a little bit about what we've been doing in my lab, and particularly some of the progress we made down there during the summer, which has been pretty exciting for us. Next week, we'll be actually having another local person, Ann Gelb from mathematics. She has some specialty in some areas of image processing and various things that I think might be of interest to astronomers and certainly to myself, since I work a lot on images, and I'm looking forward to hearing her. And then we've got some plasma physics discussion from Jim Drake at University of Maryland. I think if I go through everybody in detail, it'll take too long, but we'll be posting more information about these to make it available to everybody, and looking forward to having everybody be here for the remainder of the term. So I guess with that, I'll get the lights and introduce myself a little bit, because not everybody here knows me. It is the beginning of the fall term. There's a couple of new people here. I want to do that one, I think. All right. So I was a little bit poking some fun with my title here, since most of the work that I do involves a lot of lasers and optics and stuff. And the work I'll be focusing on today has largely to do with the portion of my work that really almost it intersects most strongly with classical questions in condensed matter, even though I'm really, by my training, more of an atomic physicist, or maybe somebody who kind of started out more in optics and photonics. So I've had a bit of a migrating journey. I started off, I got my bachelor's degree at Brigham Young University, and then moved to the University of Rochester, where I really got a serious education in everything I did not know about optics. I had a great privilege of working in ultracold quantum gas laboratory of Nick Bigelow there for a while. Took a bit, and maybe I'll mention a little bit about that in the course of the talk, because it's relevant. Got a chance to work with a lot of people at the Institute of Optics there, working on PhDs in optics, and learned a lot of the tricks that I'm now employing in my current research. Then I had the enormous privilege to go to the University of Maryland, where I got to spend basically the next 4 years working very closely, almost close to daily, with Bill Phillips, who is the Nobel laureate responsible for a good chunk of the work on laser cooling. And that was a fantastic experience. Then in 2012, I made the transition to Dartmouth. And as you'll see, it was a bit of a bumpy one initially, for all kinds of reasons. But now, finally, after years of work, we are finally at the point where the experimental apparatus that I started dreaming of 6, 7, 8 years ago has actually come into being. And it's kind of stupendous to be at that point. It'll be a little hard for me to give you a full flavor of everything. I'm going to try to really be a little bit broad in my speaking and thinking, knowing the audience. I'm also going to start off the talk. My first 2 slides have some admittedly horrible and offensive and wildly inaccurate graphics. I'm doing this a little bit on purpose. The first one is kind of a meta message before I even get started, and having to do with the schedule that I just laid out. Some of my thinking about my approach to this talk has to do with feeling slightly responsible for trying to introduce a bit more of the enormous chunk of physics that I feel like I a little bit represent here in the department of condensed matter and AMO physics. And so I'm going to try to give a flavor of that. I realize in trying to prepare this talk, it's impossible. It really is. Because it's too huge and there's too much going on. That's actually true of all of physics. The other thing, and the thing I want to point out, is this graphic is stupid. It's erroneous. There are no such divisions between disciplines anymore. Please, please, please never fall into this kind of a thinking trap. Really, like, if anything I've experienced has come to the fore is I work at the intersection of several different kinds of fields. I don't know what bucket I fall in. I think most people who work here feel the same way. So don't label somebody too rapidly as being in one field or another. We're all, I think, at times increasingly interdisciplinary. And I'll try to keep that in mind as I talk to you. Okay, my next horrible slide is a more focused horrible slide. And this is going to be my absolutely, utterly inept attempt to give you a feel of why I'm trying to do what I'm doing and how that fits in the context of condensed matter physics at large. I sat down just to organize my own thoughts for this talk and think, why am I attempting to do what I'm doing? And where does it fit into this stuff? And I kind of had these two plot axes in my mind in terms of thinking about the kinds of problems that are often coming up in discussions of condensed matter physics these days. And I like the comic XKCD rather a lot, and I didn't quite get a chance to do this in sketch form like he often does. But on the one axis, thinking of sort of classifying problems or models in terms of how robust our physical theory is that describes them, ranging from, okay, up in this upper corner here, I put the ideal gas, because that was the only system I could think of where I felt I could almost maybe claim probably it's fully understood and fully explored. I don't think anything else actually falls in that category, maybe nothing does. And so I kind of laid out a few things here, 2 points on this graph. I think a lot of the problems that we end up working on have this nice orderly progression along this mid-axis. Maybe it's the main sequence for condensed matter problems. Up on the upper side here, we have some more unusual cases where every once in a while somebody comes up with something stupendously clever or unusual, unexpected, can solve some problem with the math, but for some reason or another we just haven't actually been able to make contact with it in experiment. And on the other end of things, which happens a lot in condensed matter, ridiculously frequently, somebody's messing around in the lab and says, "What was that?" And it happens over and over and over and over again. To the point now, I think most people anywhere in contact with this have gotten to, it feels like we expect the unexpected. Anytime you get into any new piece of the parameter space, weird things happen, unexpected things happen, new phenomena show up that nobody guessed were going to be there. Suddenly, new theory things just shoot out of whatever you were calculating that you weren't even trying to do. And that really makes this fun, but also bewildering and complex. I'm going to give you a little bit of a flavor that every single one of these topics I've stuck up here in some probably utterly inappropriate place covers a huge swath of even the axes I've shown in terms of what we know about it and how well we can control it. The only reason I really put this up here is I'm kind of principally focused. My drive in what I'm going to talk to you about today in our work is trying to grab a few of these things way up here that have long been just considered toy models and actually bring them into realization and test them. That's one aspect. Also, some of the work that we're trying to do is to create some kind of physical realization of materials that are known to exist that we totally, well, not totally, largely don't understand, are struggling to develop adequate theoretical tools to grapple with and maybe feed that back into theory. Hopefully we'll have some success at that. I'll tell you how we're going to attempt that. And to further illustrate a bit of the sense of adventure one probably has to have in this arena, the material that we work with in my lab is lithium. And at one point, preparing some colloquium, I don't even know which one I gave a year or two ago, I did a Google search for lithium phase diagram, thinking I was just going to explain a little bit about how we create the atomic effusive sources for the experiment and explain some of that. And this came up. And I didn't even know this. I think maybe at some level I've encountered things like this. But this is a plot of the phase diagram of lithium as a function of temperature and pressure. There's a superconducting phase in there at high pressure. And there's actually some phases in here, I'm not going to go into this, but they were totally unexpected crystal arrangements that no one had ever previously expected to exist theoretically, and just massive surprise there. A lot of the oddities in here actually have to do with quantum effects. And so the other takeaway point for my pausing on this topic is what I'm going to tell you today is about a particular journey, experimentally, taking some matter, this block of stuff, and somehow transforming it into a dilute, ultra-cold gas in the interest of seeing quantum effects. It's not the only way to do this. To see quantum effects, what you need to do is basically get the phase space density of your system high enough. So you can either sort of hold the density constant and you just get ridiculously cold, or maybe you stay at sort of more typical temperatures and just crank up the density to ridiculous levels. So things on the opposite extreme are lots of astrophysical objects, neutron stars, white dwarfs. Dwarfs, right. I have to think about that. And exotic other sorts of things that have been dreamed up. So these sorts of phenomena, materials, are all over the spectrum of physics, and really it's a particularly malleable and controllable version of these materials that I'm specializing in working with. And really, it involves taking these chunks of stuff, melting them, getting a vapor, and then using lasers to cool them down to ridiculously low temperatures. Okay, that is as much as I think I can indulge in such discussion at the moment. And so now I'm going to, I guess, be even a little bit more self-serving and describe in rough form the journey that has occurred over the last 6 years in the basement of Wilder to get from the beginnings of this project to where we stand today. And I'm going to begin by just telling you a little bit about what it takes to actually make an ultra-cold quantum gas. It's a little hard to wrap your brain around sometimes. To begin with, everything we build is extremely sensitive to vibration, motion, etc. And that was one of the first things I talked to Alex about when I was thinking about setting things up here. There's a discussion of taking the third floor lab or the basement. Basement, no question. Why? Well, even the lasers that we work with to do the laser cooling, manipulate everything, quick running the numbers on things, basically to have the sort of spectral stability you need to address atomic transitions. If the length of that laser cavity varies by 5 nanometers, you're toast. And so that's already a pretty stringent constraint. It's actually not that bad if you're stabilizing things with piezo's. I was more concerned because I had in the back of my head a little bit of a goofy idea that I'll only tell you a little bit about today, which was to build narrow line ultra-stable optical cavities as a mechanism for manipulating these ultra-cold gases. And in this case, a movement of 50 picometers in the total round trip of the cavity is enough to take it totally off resonance and ruin it. This is built, it's downstairs, it's working. I'll tell you a little bit more about it and some of the ideas in that avenue, but this is going to be the main thrust of this talk. Because of these incredible sensitivities to length scales, vibration, and all this stuff, we had to hold the temperature pretty stable. I didn't really have that much trouble getting the vibration spec, believe it or not. Temperature was the evil thing, mostly because of engineering challenges. And I guess I won't tell you anything about those. But 2 years to meet that spec. We've got it now, but it was ridiculous. Finally, something we're not too worried about yet, but really going to need to have is cleanliness in that lab. We have a lot of high-power lasers, sensitive optics, and particularly the core piece of the chamber, the experimental system, has a very, very unusual, really state-of-the-art anti-reflection coating on it that we don't even know if we can clean. I'll tell you a little bit more about that maybe later on down the line, but there's a lot of stuff that's super, super sensitive. Given that, in 2012, Pressure of Light Symposium gave me a great excuse to come up here and visit in November. I took a look at the space. That's what I got. The graduate students got kicked out. You can still see the place where the desks were. But in my head, the vision I had for this space was something. Is this not going to do this? Come on. I'm just building suspense. Ta-da! Picture taken yesterday. If you haven't been down there recently, it looks different. I struggle sometimes to properly explain to people why it takes 5 years, usually, to build something like this. I still can't explain all of it to you today, but I'm going to try to give you a little flavor. It's been quite a journey. All right, so there's a lot there. I won't have time to explain it today. I'm not even going to really talk about the laser systems, which are most of what's in the background on those optical tables. There's tons of electronics, electromagnets, lots of things. I'm going to skip all of that. Another view of the system, this is actually looking out the door that goes to where you maybe, if you've even been to the basement. The basement hall's outside that door. And that's what you see as you walk in the lab. So there's just thousands and thousands of pieces of equipment required to get these things working, stabilize them, orchestrate the sequence of events that I'm going to describe to you that's required to take a chunk of lithium and bring it to quantum degeneracy. Okay, so if you actually go in the lab, and you get up on a ladder, and you look down at the core of the experimental system, this is what it looks like today. And so I really can't point my finger at this and tell you how it works. What I'm going to do instead is give you a virtual tour. Because when you're building something this complicated, you're not going to just sort of make it up on the fly or even do it on paper. So we have computer models of how this all goes together. And that's kind of the main assembly model that we've got that we're working from right now. And you notice mostly that there's just these structures with the optical breadboards for all the lasers to be shot into the chamber and all that. Not going to really worry about that. Let's take that away. And inside of that is the vacuum chamber, associated pumps, and everything else. Now you can start to see a bit more of what the structures are. And bring that in close. I've sort of highlighted some places where the beams are actually going in various viewports. The bulk of this still is not even the interesting stuff. All this stuff in the back end is vacuum equipment. Why do we have to do that? Well, if I'm going to cool something down, a gas to a millionth of a degree, billionth of a degree above absolute zero, it's not going to be able to come into contact with anything. The inside of this chamber has to be evacuated down to whatever, 10 to the minus 14 atmosphere. At a range where the mean free path of the molecules inside that chamber is 10 to the 5 kilometers, I believe, is what it is. Which is still not as good as the vacuum in interplanetary space, but it's close. So that's what all these things are doing, and again, I'm not going to tell you all that, but that's a ton of work in the front end of this as well. And maybe more to the point, and Jan can attest to this, some of the challenge of why this takes so long is keeping this thing clean enough to get to pressures that low is also very challenging. Let's get rid of that though. That's not as interesting. Okay, dialing in a little bit closer. Now mostly what you're seeing, you can kind of see a little bit of the real experimental chamber, but around this thing is a lot of superstructure supporting magnet coils and other things. And again, this is very careful. We need control of magnetic fields in this experiment, and pretty good control. Maybe not something that is quite as state-of-the-art or as large fields as in some of the other groups here, but a little challenging nevertheless. And all of this has to be mounted in a way that, again, we have to meet these vibration standards. It's hard, especially when these are water-cooled electromagnets. They're vibrating. We found out early on we needed to mechanically decouple the magnet coils from the chamber to be able to accomplish what we needed to do. But we're not going to talk about that. Throw away all the mechanical engineering. That's not physics. Kind of, right? No, I mean, I like that stuff. But okay, so now I'm going to begin the walkthrough. What is the journey that a lithium atom goes on in the process of traveling from this chunk of macroscopic matter to this very dilute little quantum cloud that we're going to create in the end? Well, it starts off over here in this left-hand side of the chamber, which is a so-called 2D magneto-optical trap. This is a really unusual design. I wish I could tell you a little bit more about what we did in pulling this off. I'll tell you some highlights at least. So there are two sources in here, one at the top with one of the isotopes, lithium-6. That's the fermionic isotope. It's a composite fermion. The bottom one is a bosonic isotope, lithium-7. We heat these things up with these cartridge heaters in the center up to 700 or so Kelvin. The sample's lithium, liquid lithium at that point. Looks something like that. This is tricky. Heating something up that hot creates a lot of contamination usually. It's actually pretty hard to purify lithium. You expose it to air, it reacts with even the nitrogen, let alone having lithium hydride. So successfully loading this thing and developing procedures to do that was more interesting and difficult than I expected it to be. We had some kind of fun adventures I wish I could tell you a bit more about. I've decided not to in the interest of time. If you've ever handled mercury and you have a bit of a sense of how weirdly it behaves, I mean, maybe you don't put it in your hand. but it's got a really high surface tension. Liquid metals are a little bit unusual in how they behave. They don't quite act like water. Lithium is much stranger still because its density is immensely less than that of mercury. We found out that it's actually quite perfectly possible to create an inverted liquid alkali metal source. We wouldn't have been able to pull this off without looking up a lot of references for things developed in the plasma physics field for tokamaks and stuff. But this is something else that had never been done, and we successfully pulled off for this. To stay on time, I'm not going to digress into why that's actually important, other than to say keeping the vacuum pressure sufficiently low relies on how this is designed. Okay. This is a little bit more of an indication of what's going on once we start the system operating. There's just a vapor of lithium coming off of the sort of business end of these sources and flying off into this space where we've directed laser beams coming in from these directions, which exert a force. They're flying through that space with a most probable velocity of 1,000 meters per second. That's actually so fast that they don't even see these laser beams because they're Doppler shifted so far out of resonance. It's only the very slowest atoms coming off of these sources that actually interact with the lasers at the frequency we've set them. And we capture the slowest moving ones, and you notice this source is angled slightly. This 2D MOT can only take out the velocity component in the direction of the laser beams. We sort of deliberately take out the transverse velocity, leaving a little bit of the longitudinal velocity to let it fly through this hole, creating a cold atomic beam that goes through this little aperture into the other part of the system. This is also an important simplifying technical detail to be able to keep the vacuum pressure lower on the other side and also make sure that we can use this axis for other things. Most often people actually use a laser beam, another laser beam, to push the atoms through this hole. We opted not to do that for reasons which may be evident later on, although I won't go into detail. All right. This rendering, unfortunately, came out a little bit more busy. I've added in now the main experimental chamber attached on the end of the 2D magneto-optical trap. And here we've got a standard 6-beam magneto-optical trap. Now forces from all directions and a magnetic quadrupole field combining make it so that an atom in this space, no matter which direction it's moving, it feels a drag force opposite its direction of motion. And if it's not sitting at the geometric center, it feels a force that moves it toward the center. Those two things together allow it to set it up so that the lithium atoms collect at the center and are cooled down to essentially 1 millikelvin. We get them a little bit lower with techniques that Yanping worked hard on for a good while, and I decided we don't have time to talk about. But once we move from this laser cooling stage, you can't see the atoms anymore. We use so-called absorption imaging, which I'm only going to briefly describe, but most of the remaining images I'll show you from actual experimental data will use this technique, which, long story short, I have a quantum gas. I shine a laser beam through this space, which is resonant with that gas. There's a shadow. Absorb, scatter, there's a shadow. The shadow depth is proportional to the density. We do some processing on that. It's not that simple. And we get a map where the red is high density, blue is low density. So keep that in mind as you see the images I'll show you later on. All right. This is all actually not that hard to do. Pushing the button on this thing apparently is the hard thing to do. The trickier part is the next step. This was where I started to get more worried. This is where more of the effort has to go in and where things get touchy. And this took a while, and a little while longer than I expected. Once you've got those atoms pre-cooled, you can turn on a conservative potential to trap them in. In our case, what we do is use focused laser beams. Why does that work? Well, atoms are neutral, and so you can't just apply static electric fields to them to do something. But oscillating electric fields polarize them, and polarize them in a way that, depending on the frequency of the light with respect to the resonance, you basically end up having an attractive force or repulsive force from any region in space where there's an intensity maximum. So-called optical dipole trap. And this is a really interesting thing. I mean, this is something I thought about digressing onto and chose not to. But the first stage of the cooling is resonant interaction with light, scattering, second stage is off-resonant dispersive interaction. And that's pretty important. Both phenomena always exist, and we end up limited in how cold we can get in some cases by residual scattering, even from these lasers I'll tell you about in a second. But that ends up ultimately not being a limit if you construct things correctly. Come on. I'm just going to stand back here. So what does this actually look like? Kind of showed you on the other slide the picture of this larger cloud. It's actually several millimeters in diameter, large to me. That's a several millimeter diameter cloud at a temperature of around 100 microkelvin. That doesn't mean a lot to you, but it's pretty cold. Not as cold as we need to get, but pretty cold. We focus these lasers into the space in the middle of this cloud. And if the lasers are intense enough, then atoms within that area can't escape the trap when we shut off the cooling lasers. That's essentially what you're seeing in this upper sequence of images. This is, I didn't put the times on here. This is basically what this looks like the moment that we have the laser cooling shut off. I'm aiming with my hand. Here's the pointer. Laser cooling shut off, and the atoms that are starting to collect in the trap. 1 millisecond later, these are starting to disperse, but the ones that were in the trap are still there. Another millisecond later, basically everything that wasn't trapped is gone. You notice this actually fairly extended at this point. And after, I forget, this is another millisecond or even longer than that. I'll have to, oh, this is, I think, 10, this is a while later. This is what it ends up looking like. At the intersection of two laser beams we fired through this space, there's a very high intensity point that the atoms collect in. There are some way out here in the wings along the lasers where the intensity is not so great. That's a bit of an indication that the temperature is still pretty high. The depth of this trap is about a millikelvin. And so there's still atoms floating out there with a lot of energy comparatively to where we eventually want to go. To get anywhere with this, we need metrics to tell us how cold we are. We want to know when we're quantum degenerate. How are we going to do this? I already told you we can at least take pictures. But if we want to get clever, what we want to do then is measure the temperature. We know the density. We can figure out the phase space density. We know when we reach quantum degeneracy. This is a sequence of images where what we've done, this is basically the same view, a little bit later in time. Some of the hottest atoms have left. I'll talk about evaporation in a minute. Turn off the trap, and the atoms freely expand. It doesn't really take a genius to figure out that if it's hotter, it's going to expand faster. Because basically, at this point, it's still a classical gas. Maxwell-Boltzmann distribution still holds pretty well. And you can just calculate exactly what it's supposed to be. Look how big this thing is after, I think this is 300 microseconds. When we've let it go, you know what the RMS velocity is. You project that back, you have a temperature. In this case, I know Yan Ping told me, I think it's something on the order of still 100 or a little bit below that in microkelvin. Something like that. Okay, we need to get colder.
How many atoms?
Oh, yeah, actually good question. I actually had that in some notes to say, so thanks for asking. This initial laser-cooled cloud has in it somewhere a few 10 to the 8 atoms. And if you think about it, a few 10 to the 8 atoms in a millimeter-sized ball is basically nothing. It's more empty space than in most vacuum chambers. You know, you have to work pretty hard to get to a vacuum that's lower density than that in the first place. So it's really dilute. Once we actually do this initial capture into the so-called dipole trap, the optical dipole trap, it's a few 10 to the 6. So we don't get a large fraction of the atoms into there. Maybe we're getting 10 to the 7. We're getting a little bit better at it lately. But still, tens of millions at best. In the next stage, ultimately, what we have to do, I'm not going to trust this thing anymore. I should have used my own. Oh, there we go. I'll tell you in a minute how the cooling works, but this is an indication of what we get if we succeed. This is that sequence I just showed you. I guess that was up to 200 microseconds. This I actually put the time wiggles on, thank goodness. This is all really new data. The only reason you're seeing any of this is because Yan Ping's been working hard, so sorry if it's not as digested as it ought to be. So these look somewhat similar. You notice this one's already smaller. It's partly because there are fewer atoms, but actually mostly because it's colder. The big difference is if we shut off the trapping potential, this one rapidly expands. This one almost does nothing. And it is down, I think this one probably was already quantum degenerate, right? This is below T over TF. Come on. Oh, I skipped? All right, so I think I was going to talk a little bit more about the geometry here, but I think let's not. I guess I'll only say we have more than one way of doing this. I'm showing you data from the simplest version of this trap that we put together in order to kind of facilitate moving on and getting some science done. You see in this picture of the chamber, there is this optical cavity that I mentioned before. We actually can use it as an optical dipole trap as well by injecting light in through these mirrors and getting the circulating power in that cavity up to, the hundreds of watts necessary. So by the way, yeah, so this is like, I should have mentioned, this is welding grade lasers. You know, if one of these things misses, these things are focused to a spot size and have a high enough power that if it was just out here on the table, it would just be cutting through the table. So it's a little bit funny to actually think about, you can do that. I mean, you just blow through a table or really almost any material, but then you fire it at a dilute gas and it's cold. A little paradoxical, but fun.
Kevin, those images, do you destroy the sample when you take an image, or is that the same sample over and over?
This is a repeat iteration of the experiment. So I'm kind of describing this process of taking the atoms and cooling them down and doing something. At the moment, we do this every single time and create a new ensemble of atoms. Take an image and then they're gone.
Right.
Exactly for the reason that one photon striking one of those lithium atoms imparts enough recoil energy to it. Even if it's just, strikes the atom and is randomly scattered in some direction, the energy associated with that recoil is an order of magnitude greater than the average temperature when we get it to this point. It's not, and that's basically why we have to go away from the laser cooling. We go down in the laser cooling to as cold as you can possibly go until you hit that recoil limit, and then you go no further. And that's what you got. So whatever the wavelength of light is you're using to cool, whatever the mass of the atom is that you're using, that sets a recoil limit. You're not going to get any colder than that with laser cooling. But then you do that. That's the next point. And this one's actually way easier to understand and explain than laser cooling. I wish I could tell you more about laser cooling. I always want to in these talks. It really is simple as you've got something in a bucket, gas banging around against the walls, and somehow you contrive to let the hottest ones leave. Actually, it's not quite that simple. You need one more ingredient. If you just have a non-interacting gas, which is usually what you solve in statistical mechanics if you're ever playing around with calculations of Bose gases or Fermi gases, you get nothing. Well, basically you lose the hottest atoms, but you never increase the phase space density of the sample because it doesn't re-equilibrate. It's like, they never know that they're there. The lower energy atoms don't know that the hotter ones are gone. It doesn't change a thing about what happens. So the necessary ingredient, one of the most challenging things in this experiment is we have to have enough interaction between the atoms for them to thermalize. As we get rid of the hottest ones, then the temperature goes down. Yep. Why is this hard? Well, lithium, for all the other good things about it that I could tell you that might be more apparent when I tell you about the experiments we're planning, it's horrible in that it really has a very, very weak interaction, unless you play some very specific games. Furthermore, these are fermions. If you have spin polarized fermions at very, very, very low energies, so it's purely S-wave interactions, you can't have collisions. It's forbidden. So this is not a spin polarized gas of fermions. There are actually a number of different ground state spin configurations for, there are 6 spin states in the ground state manifold of lithium. We're using the 2 lowest energy ones. So we have 2 groups of atoms with different spin that they're distinguishable, and those 2 groups can collide with each other, but not with atoms of their own spin type. Still, even to get that to work, we actually have to increase the magnetic field in the area of the atoms to actually mess with the internal structure of the lithium atoms so that they scatter off each other more. I thought about talking about this phenomenon, which is referred to as a Feshbach resonance, and decided it wasn't going to fit in the talk. But it's one of the most important knobs we have, and I actually will come back to talk about it a little bit, but I won't explain how it works. Assuming you get this right, you start off with enough atoms at enough initial density to be able to have this equilibration proceed, and you're not heating things by having things shake too much. I told you that the vibration constraints are pretty serious. Then you can carefully, gently, cautiously edge it down to much, much lower temperatures. And when you get the recipe right, it just works. It's really hard to get the recipe right. But when you got it, you got it.
Are you losing another magnitude of atoms in the evaporative cooling?
How many atoms are we losing?
Yeah.
At this point, it depends on how far we cool. So if we just want to cool down to, actually, is it my next slide? Oh, there we go. I wanted to have a slightly more well-digested plot, but the only reason you have this, again, thanks to campaign. If we lower the power of the laser, it makes the trap progressively shallower, and the hottest atoms are able to spill out and leave, and the temperature cools down. Interestingly, for various reasons, if you actually try to compute what the temperature would be as a function of the depth of the trap, it almost always ends up that you have a cloud with a temperature that's 1/10 the depth of the trap. We always talk about the trap depth in terms of temperature units for convenience reasons. The trap starts off with a depth of about 1 millikelvin, and we ramp it down ultimately something more in the 10 microkelvin range, which puts the temperature of the cloud down to 1 or 2 microkelvin. And at this number of atoms, which is about 5 times 10 to the 5, once we get down to this level, the Fermi temperature is about 2 microkelvin. And this is, we got this working actually, what was it, beginning of August-ish? But even though I was pretty sure we had it right, it took us another month to get through all of the calibrations and checks to be sure that we really were getting below this limit, because it's not that obvious. Some of you may know a little bit.
Kevin, on the previous slide, the vertical one was temperature divided by Fermi temperature.
Oh yes, I'm sorry, I should have, I committed the astronomer's sin of never explaining the axes.
That's phenomenal, thank you.
Yes, so this is the temperature divided by the Fermi temperature. The Fermi temperature is a function of the atom number and the trapping potential depth and shape, which is changing as we change the laser power. So it's not super straightforward to do all of this. But this is ultimately the fitness parameter we care about, because that's what determines when the quantum many-body effects we're interested in are going to kick in. And now I'm going to say that comment. That's what I'm going to come back to. So yes, so this is indicating that 1 is already basically Fermi degenerate. It's too hot to see most of the phenomena we're really interested in, but that's the point at which you really, really, really cannot ignore anymore that these are indistinguishable particles that have to be antisymmetric. This is just not an ideal gas in any way, shape, or form anymore. And the deeper you can go, the better. But as Roberto could tell you at great length, there are reasons why this is extraordinarily difficult to go colder. And I can't go into that as much. I do want to mention something, though, because I think by now, most people probably know a little bit about at least Bose-Einstein condensation, and have seen the nice pictures that were generated early on at MIT of what this looks like as you cool down, and there's this, I should have stuck it on the slide, because this picture actually doesn't show it, interestingly. But in these sorts of systems where you have essentially a harmonic potential that you're cooling things down in, there is a really clear point at which the Bose-Einstein condensate forms. And at the center of the trapping potential, there's a density spike that just jumps up. And it's very clear that there's something there that is different from the remainder of the gas. Doesn't happen with fermions. And if you've thought about quantum statistical mechanics for a little while, you know why. It's just that the fermions basically occupy every available state, and that sets some momentum and spatial distribution, and it just basically doesn't change anymore. Once you get down to near the Fermi temperature, the shape is set, and there's just no signature that you're there. which is a little disappointing because it's actually harder to do than for the Bose-Einstein condensate. I guess, yeah, I was going to point out that in our data you will see, if I showed you more, that as we cool, essentially you just asymptotically approach this sort of fixed shape and it doesn't just go anywhere after that. Another detail, which I think I have, I'm going to skip because I'm going to come back. No, hold on. Where did I thought I had, did I skip past the slide with, oh yeah, I wanted to talk about this one a little bit more. There's another interesting difference between this and the Bose-Einstein condensate in terms of identifying what's going on. This series of images is multiple runs of the experiment, where what we've changed is how much we've reduced the laser power at the end of the whole sequence. But we have not just held the atoms, we've released them and allowed them to expand for 300 microseconds. So we're seeing a momentum distribution of the atoms, and that's, as I said, how we get the temperature. If you do this with bosons, it looks very different. In this case where the atoms are hot, they'll expand isotropically because the momentum distribution is isotropic. For a Bose-Einstein condensate, that ends up not being true. You think of the giant wave function that this thing is forming. If it's asymmetric like this, it's more tightly confined in one direction, expands more rapidly in the tightly confined transverse direction and less rapidly in the long direction. That doesn't happen here. So again, we don't have this clear-cut signature of the quantum degenerate limit. Okay, I guess I was going to try to end early. I'm not doing so good. I'm not going to talk about the cavity. Some other day. Okay, so that's kind of where we are now. And that really was by far the hardest portion of the sequence of things that we needed to do to get this to work. We now have a quantum degenerate sample. We can start to play with questions in physics. But not quite yet. This whole structure we constructed to cool things down is a problem. It's very much in the way of all the tools that we need to actually conduct the experiments. I won't tell you all the reasons why, but maybe it'll be obvious. So we actually have to move the atoms. We take another beam, fired in from this end, focused into here. We shut off the lasers that we were using to confine the atoms, that we originally did the cooling, and we move the whole thing over into this glass cell we refer to as the science cell, where, well, because that's where the science is going to happen. We should have a more creative name. I don't know. What this buys us is, one, no metallic structures nearby to mess around with the magnetic fields that we need to apply to control the interactions of the atoms. Two, much closer access for imaging systems and projection systems to focus lasers to very, very tiny points and have very, very high imaging resolution. And we're going to use that capability to do some things that have never been done before with quantum gases. Anything more I want to say about that? Yeah, so we still need magnetic fields to control the interactions.
Do you have photographs of what a atoms looks like in the science prism?
We have not moved it there yet. That's what they're doing right now.
Okay.
How's it going? I've hardly talked to them this week because I've been so busy.
How do you get them to go over there, and how do you stop them when they get there?
So this beam, I glossed over, maybe trying to be too quick. This is an optical dipole trap, just like the trap that we use to confine the atoms to do the cooling. So it's another laser, some differences to it, but it's still focused, and there is a point in space, or region in space, where there's an intensity maximum. This is what's sometimes referred to as optical tweezers. Basically, we get that in the location where the atoms are. They're attracted to that focal point. We turn off the other laser so that it's not also pulling on them. And we just move that focus, and the atoms come right along.
Oh, so you just pull the focus, and the little spot moves over there and punches it.
Now, it's not trivial to do that either.
I wouldn't think so.
That capability has been the subject of significant work in 2 undergraduate theses so far, et cetera. The thing's basically working. We just need to finish dialing it all in. We've got a few interesting technical issues, but not interesting enough to talk about now.
Do you expect to lose any more atoms when you move it? Like, what's the size of the little resulting?
I'll go a little bit to the side because it is a bit of an interesting point. I showed you so far images that we cooled to quantum degeneracy in that initial chamber that we've been talking about so far. When we do this, we actually won't cool them to quantum degeneracy before we move them, because there is always some heating, because you just can't do it perfectly. I mean, if you could move everything perfectly smoothly, nothing going wrong, maybe you could move an ultracold ensemble 30 centimeters without shaking it and heating it too much. But the temperature of this thing is a microkelvin. And so if you add enough heat to bring it up to 2 microkelvin, you're kind of toast. You've really ruined the thing. But if we just cool it down just cold enough to be able to grab it with this laser, just enough for this laser to grab it and move it, maybe 10 microkelvin, 20 microkelvin, it doesn't matter if we heat it up by 1 microkelvin. We evaporate again once we get there. So that's the trick. If we cool it all the way down first and then move it, no good. We just cool it enough that we can move it, and then we finish cooling it.
So you'll still be ending up with about 10 to the 5th.
Yeah.
So atoms.
It'll still be about the same atom number. Yep.
Does that just scale with the first part of the experimental setup? Just run that 10 times longer, you'll get a cloud at the end that's like 10 to the 6th? Is there like an upper limit on, sorry.
Let me answer your question later. It's a lot more complicated than that, but there are some hard limits and some various things. It's pretty hard to, you can do better this, but maybe not more than an order of magnitude or possibly 2. 3-body recombination, lots of things like that. Okay, so what are we going to do with this thing? I've only got 5-ish minutes left. I really want to talk about, why would you go to all this trouble? It's 5 years of my life, 6 years of my life, and tremendous effort and money to do this. And it's not just for bragging rights, I hope. What we're hoping to do is explore the properties of some of these quantum phases, and particularly use a technique that's not been applied ever to fermionic systems that I was only just barely come up with when I was at NIST a few years back. We're going to actually create a ring-shaped trap for these atoms and use transport and transport properties as a mechanism to probe the underlying behavior of the quantum system. I'm going to do this really fast. Any superfluid, most of these systems have some kind of an order parameter. There's some kind of a quantization condition that is always enforced. Sometimes it's a relatively simple one. I should explain this one, but I'm out of time. You have to have single valuedness of the wave function or the order parameter, whatever it is, on these things. And that ends up resulting in quantized circulation states. The plain vanilla versions of these are pretty straightforward. I think we've anchored that we can do these sorts of things. The things we're going to be looking for in this experiment is stirring this up, starting the flow going, and looking at what stage we actually see jumps in the circulation from not circulating to circulating with 1 quantum to et cetera, or doing the converse, having something that's circulating and looking at what point or what strength of perturbation it becomes unstable and drops. What information do we get from that? Well, one, we get the information that's a superfluid, and sometimes that alone is really not trivial, especially for some of the more exotic, unconventional superfluid phases that we're going to be hunting for. And that already will be big, if we even see evidence of a persistent current. If we got that, we also get information about basically whatever the mechanism that's causing there to be superfluidity. If it's a Bose-Einstein condensate, you get information about what the chemical potential is. If it's a paired Fermi gas of some sort, BCS or otherwise, then you learn about the pairing gap. If you start seeing what sorts of things end up breaking the system or causing instabilities. And we can start to probe that and map that using this. And so basically try to figure out what these sorts of response curves are going to look like. We make measurements and we start to learn a bit about what is really going on in this quantum many-body system. That's a really short explanation. Okay, I'm not going to explain how we actually know that there's a persistent current. Oh, this is a fun slide, and just an aside, this isn't all we're going to do in this system. My main interest is in probing this sort of really fundamental many-body physics. But there's some interesting things to be learned about superfluid dynamics as well. This is a fun simulation done by a collaborator of mine, kind of simulating the system that we had at NIST a while back, which was a Bose-Einstein condensate of sodium atoms. And what you saw at the beginning of that video was basically a perturbation, a stirring of this thing. And rather than having something like nice and well-behaved like a phase slip happen, a bunch of vortices were formed. And that's what these things are. And I kind of like this mostly because as you watch this go around the simulation, it really drives home that these vortices are quasi-particle excitations. They really behave like little particles bouncing around in there and interacting with each other. And there's some interesting things to be explored with that we'll probably do in the mix of everything else. Yeah, sorry I cut that off. It's a long simulation, actually. There's more fun stuff, but no time. I wanted to, before finishing, try to actually explain in some more detail about one of the sort of flagship things that we want to do. And that requires explaining a little bit about superfluidity or superconductivity in fermions, in fermionic systems. Regular garden variety superconductors, if that even makes sense to say such a thing, basically have something happen where the electrons in the system, obviously there's going to be spin up, spin down if there's no external magnetic field. You've got some Fermi energy in the system, and hopefully most people have got some broad idea of the fact that there's an attractive interaction. The fermions pair, they form a quasi-particle that is its own entity, and it doesn't have to obey fermionic statistics anymore, and so it actually can behave effectively bosonic. It has a bosonic degree of freedom if we want to be a little bit more careful in talking about that. And this Cooper pair superfluid, essentially, can flow with no resistance. We understand pretty well how that works. And our first stop in this experiment is to show that we can see this and measure it and characterize everything having to do with a BCS superfluid. I won't say that much about the BCS crossover in the interest of time. The idea is that there are actually a lot of much more exotic things that can happen, of which I will describe one. And we'll be able to see, hopefully, other mechanisms, types of systems where something strange can happen, that there's an ordering of these quantum particles that just spontaneously happens when you're cold enough, or whatever the criterion is. Okay, I was going to talk about this because it's kind of fun, but we'll skip it. This is more of what I want to nail before I run out of time. There is an unusual superfluid phase that was predicted decades ago. And the story of this, what's supposed to happen here, goes something like this. And this is going to make a little bit of an assumption that you do have some kind of a mental idea of what happens in a BCS superfluid. Sorry if that's a bit of a jump now. For a BCS superfluid, the Fermi energies of the two spin states have to match. The pairing occurs at sort of the outer shell of, this is a depiction of basically momentum space and population of fermions at different points in, at least as far as this diagram is concerned. It goes out to some radius because the fermions are filling out in these levels up to some point until they reach a maximum level, and then that's it. They don't fill any further. Usually, you would say that the Fermi energies have to match in order to have electrons at the surfaces pair and then form that Cooper pair superfluid. That's a supposition that basically holds true most of the time. If you tip things over and you polarize this thing, you make it so that there are way more spin-up electrons than spin-down, it changes the Fermi energies, and the ones at the surface can't pair, and they can't form a superfluid. It breaks. It's not a superconductor. But that's not the end of the story. Fortunately, it's way more interesting. There's a prediction that under certain circumstances, you can actually have something result in, there's an instability. There's a shift that, this central circle indicates kind of the momentum distribution of the spin-down electrons, or lithium, whatever you're talking about. And the outer circle represents the momentum distribution of the spin-up particles. And normally it would be centered around 0. It kind of makes sense from an energetic viewpoint that that's what you're supposed to do. If you're trying to minimize the energy of the system, that's what you usually expect. But if there's a mechanism for pairing, and you can lower the energy somehow that way, if you get into a regime where that ends up being favorable, it'll actually just pull this thing off to the side. It shifts. So that these populations of the spin up and spin down particles don't stay with an average zero momentum anymore. And that brings the Fermi surfaces into contact in some region, and pairing can happen there. And the resulting pairs and superfluid is weird and kind of cool. I'm not going to talk about this bit of the phase diagram for it. I'm more going to be, I'm going to come back to contact with what we think we're going to see when we do this. So if there is this shift in the momenta, the average momenta, that means things are moving. This is a quantum system, wave functions. It's a traveling wave. Basically, you will wind up seeing a modulation of the system in some direction that it will either be a spin density wave, meaning as a function of position, you have an oscillation in which spin state is present, or it's usually referred to as a charge density wave because it's usually superconductors. For us, it's a neutral superfluid, so I'll just say density wave. And there's an actual variation in the density of the material, but it's along a direction. There's a broken symmetry here. For a BCS superfluid, there's no preferred direction in space. For a fully ferrule Larkin of Chinnikov, it's still such a mouthful, there's a broken symmetry. There's a preferred direction. What sets that direction? Well, it kind of depends, but the geometry of the system plays a role. That's something we can use. That's a reason for the ring. If we can force it to go azimuthally, then that flow is going around the ring. If we start to drive currents around this thing, then, all right, long story short, when you would normally expect to see jumps in the circulation at integer values of the quantum of circulation, you basically, again, figure out whatever the minimum angular momentum that these particles can have going around a circle of some given radius. That sets some angular momentum scale. Because this is a really weird kind of quasi-particle system in a different kind of order, we actually should see jumps in the circulation, half quantum jumps twice as often. We should be able to see this. And even if we can't directly see the spin density wave, charge density wave that goes around the ring when this symmetry is broken, we should be able to see this. This might be hard, we should see that. And that will be the very first time that this has ever been observed. I wish I could tell you more of why this is hard and why no one's seen it yet. But it's believed to be important for a lot of other physical systems where this phenomenon plays a role, certain types of more exotic superconductors. It is kind of a toy model, but we can realize something in this ultra-cold quantum gas that's a super stripped down, simplified realization of a quantum system that used to be thought of as just a toy model until recently. All right. There are more things we expect to be able to do with lattice systems and all sorts of other things. This is kind of the roadmap we're looking for in the future, and I am almost done here. The next thing we expect to see, now that we've hit this milestone and we've got quantum degeneracy, pretty quickly, I think, we're going to start punching down through this list. Our first stop is showing that we can create persistent currents in a so-called molecular BEC. We pair those lithium atoms into molecules. Those are bosons. Bose-Einstein condensate. We can validate all the tools I just described for testing the properties of the system. Then we'll start messing with the interactions and see what happens as we go smoothly between that molecular BEC and the so-called, the BCS superfluid, the well-known one, the balanced one. Then we break it. We polarize it. And we start to see what happens there. And on and on. We can create lattices. We can probably do spin orbit coupling. We can start exploring this vast space of things that is still pretty mysterious and showing all kinds of surprises in the whole realm of condensed matter physics. That's the main thrust of what we are currently trying to do in my lab, is to learn something about these sorts of systems. There are other things we're expecting to do along the way and on the side, but we'll save that for another day. This is really, there we go. So, With that, a thanks to the many students who have been involved in shepherding this thing along from its inception to its current form. There's been a lot of construction and work and modeling and design and everything. From first couple of undergraduates who joined me and were really responsible for a lot of the grunt work of getting some of the main systems in place, and then some of the later ones who worked on that movable dipole trap system that was described. And the set of graduate students I have now, primarily Yan Ping, he's probably the only one who fully knows how to run the system at this point. And some great contributions made by Jesse, who is not here at the moment, but worked very much on that optical cavity, which I expect to be an increasing portion of the work we'll be doing, and maybe it will be a subject of future discussion. So that's what the future holds. Thank you for letting me talk. I've gone long, but we have the tea, and I want to be sensitive to people who don't want to stick around a long time. I'm always here. I'd like to answer questions, but let's let anybody who's really busy run. So thanks. Let's just go ahead and go to the. Anybody object to that? I'll stand here and answer questions if you want. Anybody wants to go now, and I'll answer questions here.
Why don't you answer some questions?
Sure.
What sets the fundamental limits of evaporative cooling to the 1 to 2 microkelvin or fractions thereof? And how do you go lower than that in the future, or can you?
For fermions, in a nutshell, the reason why, let's see if I can distill this down really fast into a soundbite. Essentially, the cooling mechanism fails to work once you get too cold. You can't efficiently reduce the entropy because you have so few excitations in the system, and trying to somehow, you basically don't have hot atoms anymore. And the distribution of the holes and excitations in the Fermi gas, it just does not work nicely to try to evaporate any further. Evaporation works beautifully as long as it's quasi-classical or kind of near the degeneracy limit, but evaporation just is not effective anymore for fermions once you get down well below the Fermi temperature. There's more to it than that, but that's the short answer.
But let's say I have bosons and I very slowly lowered the trap depth. And I lower the trap depth enough that the bucket spills, and I shave off the top layer, and then I lower the bucket again till I shave off the next layer. And I do it in such a way that there's no heat diffusion so that the hot atoms don't heat the cold ones. It seems like there's a trade-off between lowering the trap depth too slowly, which means you're going to basically not ever cool, because you're just staying there, and lowering it too quickly so that all the hot atoms that are escaping, there's either nothing left or they're heating the cold atoms.
Maybe
so is there some trade-off or a feedback loop that you could design so that if you could watch the hot atoms somehow that we're leaving and feedback to change the laser or optical trap depth in a way to keep them cool?
I think I can give you a short answer. My first answer was focused on what I think is more interesting theoretical limit on the cooling, which you can try to work harder and harder, but the practical limit is you're never free of heating. And so you can't just go slower and slower. You can't just try to be more and more careful. You've got an ultimate limit actually set by the vacuum. If you've got this, imagine you had a 0 temperature Fermi gas. Somehow you pulled it off magically one time, and everything is just perfectly parked down in the lowest available energy levels. One background molecule flying through and knocking out one of those fermions raises the temperature immensely, and you're toast. So it's really, really hard to get to those low entropy states. There's more to it, but that's the best short answer I can give you. Sorry, I can get the back.
You have all these pictures of these, the time series of your cold cloud, and each one is a new sample. How long does it take to get each sample?
I meant to actually put like a clock up in the corner so you'd know how long the whole sequence is running. That's pretty easy to answer. So the first stage, loading the magneto-optical trap, right now 15 seconds. That's the longest-ish part, almost. The next sequence of things of moving it into the dipole trap and kind of doing that little handoff is fast. It's sub-millisecond time. The evaporation takes longer because the thermalization time is still pretty long. That typically 15 to 30 seconds. And again, that's limited by the vacuum lifetime. Right now we've got a vacuum lifetime in the chamber of something like 45 seconds or so. We're getting to a minute is good. If we had it longer, that'd be great. But the whole thing happens in basically less than a minute. Now, if we actually start conducting experiments on the thing, sometimes manipulating the ring quantum gas and allowing it time to equilibrate and doing fancier things, more time is going to be added on for that. And we may need minutes to conduct those experiments. That's typical of what I did at NIST. Is it may have been several minutes to do one run. So that's 3 minutes for a data point. Although it's a pretty robust data point with a lot of information on those images. That's the time scale. It's slower than you might think. You had a question. You can always find me, Shaker. Yeah.
This might require an answer that's too long, but I was wondering what kind of experimental procedures you have in mind for bringing these two Fermi surfaces into contact. It seems like
we don't plan to do that in a deliberate way. The idea is it should happen spontaneously. Although actually, it's an interesting angle. One way of thinking about what we're doing with confining the atoms to a quasi-1D ring is actually to increase the size of the parameter space where that instability exists, where it will shift and form that unconventional pairing. The reason why it hasn't been observed so far is that in 3D systems and most of the things that people have tried to observe this in, the part of the parameter space that is in is so tiny, like the sensitivity to polarization or the temperatures required or something is just impossible. It's partly the qualities and geometry that we're working with that will give us what I think is going to be the best shot to date to finally say, yeah, this happens. So, yeah. I'll answer questions as long as everybody wants. I just don't want to hold you here too long.
So in this sort of where the Fermi surfaces come together and make a superfluid that's going that way.
Yeah.
It's really moving.
It's actually, it's usually going bidirectionally. The two components are shifting. And it depends on the, well, in the sort of, if I'm not stirring it, if I'm not creating a persistent current, there's basically a bidirectional flow around the ring in this case. Or if it was a infinite-sized system, then there would be some broken direction and there would be flow in two directions in the different spin states. But
will this be standing waves or will it be the two superimposed?
It's actually either standing wave or traveling wave, depending on whether it's Larkinov-Chinnikov or Foldy-Farrell. That's the reason why all four names are in there. So we're hoping to explore both limits, where it's standing wave or traveling wave, and we can do that because we can break the ring, see the standing wave version, let the ring flow, and see the traveling wave version. Yeah. Oh, Lee.
Why did you decide to use lithium?
Yeah. Many reasons, none of them having to do with being easy. It's light, which means it's going to have a much larger de Broglie wavelength at a given temperature.
Yep.
That's really important for the lattice experiments, mostly because the tunneling range that you get is enhanced the lighter the particle is. It's a little challenging. Electrons would be great, that's so much lighter. But if you're going to pick an atom, pick a light one. Then the length scales over which things happen are longer, and they're more likely at scales we can actually image directly. I want to have density features like the ones I was just describing on something that's at least the size of the wavelength of light, and that's most likely to happen with a light atom. The other big reason, was that sufficient? So if I use rubidium, for example,
Yeah, just like
okay, that's not even a fermion, so I can't do it. Ytterbium has a fermionic isotope. Yeah, so if I use something heavier, then everything has to be much smaller, and I have trouble making it and measuring it. If I want to observe it, I want something as light as I can possibly get. That's kind of the benefit of these, is I really can directly image.
I mean, and the fact that, it's weakly interacting, you can completely compensate for that with a Feshbach resonance? Or?
Yeah, well, and that's the other reason, is lithium has a great Feshbach resonance. I didn't explain anything about this. The interaction strength of the atoms is tunable. if I vary the magnetic field, I can make the lithium atoms attract each other, repel each other, not interact, or go into what's called the unitary limit, where basically infinite interactions. And most atoms, you have to really control the magnetic field extremely accurately around a certain point to be able to make that work. Lithium, the range of magnetic fields is broad. It's a broad resonance. And it's technically much easier to have excellent control of the interaction strength. So that's the other really big thing. A lot of the stuff that I'm doing here is also, it's going to be the first time it will have been done with something that actually has a tunable interaction. So there's lots of avenues in which this is hitting new ground. That's one of them. There are probably other reasons I chose lithium. I have to think about it, but later.
All right, let's thank Kevin.
That's good.